today our topic of discussion is basically energy from chemicals. Energy from chemicals. So first of all, there are some reactions. There are some reactions in which heat energy, in which heat energy is released. Energy is released into the surrounding, into the surrounding. So the type of reactions in which heat energy is released into the surrounding, that type of reaction is called as, yes, Ian, that type of reaction is called as
It's called
exo,
as an exothermic reaction.
yes, that is called as exothermic reaction. Okay. So there are also some of the reactions as well. Some reactions absorb heat energy from the surrounding. Okay, from the surrounding. So that type of reactions are called as endothermic reactions, which absorb heat energy from surrounding is called endothermic reactions. Okay, so we have discussed two type of reaction. The one is exothermic reaction and the other one is endothermic reactions. Okay, so let's discuss about some of the examples which are related to endothermic reactions, and there are some examples of exothermic reactions. We are going to discuss them in detail. Okay, so this is endothermic, in which heat energy is absorbed from the surrounding, and this is exothermic, in which heat energy is released to the surrounding. Okay, so first of all, let's consider about endothermic reaction. So first of all, we know melting of ice. So in fact, in melting of ice, what actually happens, that in melting of ice, you are going from solid to liquid state. Okay, solid to liquid state. I just want to ask you whether solids are the particles of solids are having higher energy or the particles of liquid. Yes, Ayan. Which is having higher energy, solids or liquid? Yes. Whose particle is having more energy, solid or liquid?
Liquid.
Very good. So the particles of liquid, we know they are like far away from each other. So they are at higher energy. Okay. So they are at higher energy so they are basically at higher energy and they are basically at low energy. So if you are seeing that as we are going from solid to liquid, we are moving from low energy to high energy. That means we are absorbing energy. That means we are absorbing energy. So this is basically an example of endothermic reaction in which heat energy is absorbed from the surrounding. Okay, then I can give you some more example, and that is basically boiling of water. Boiling of water. Okay. So boiling of water, we know we are moving from liquid to gaseous state. So can you please tell me whether liquid is at high energy or gas is at high energy? Yes, yeah. Which is having more amount of energy, the particles of liquid or the particle of gas? Yes, yeah.
Liquid.
No, which is having more energy? Whose particle is having more energy? Gaseous part.
Gas.
Yes, because they are far away from each other. They are colliding with each other and with the wall of the containers as well. So they are basically at high energy, and this is basically low energy. So what is happening as we are going from liquid to gaseous state? The energy is increased. That means energy is absorbed. So this is also an example of endothermic reaction. Okay, then we have some more examples, and let's discuss them in detail, like decomposition of copper carbonate. Okay, when copper carbonate, this is copper carbonate, and they are decomposed because we are giving heat to it. Okay, so it is decomposed into copper oxide, and carbon dioxide gas is released. So this is decomposed and converted into copper oxide and carbon dioxide. Okay, so this is basically also an example of endothermic reaction in which heat energy is absorbed to break the bonds among copper carbonate. Okay, to break the bonds. Remember, breaking the bonds is basically an endothermic reaction. So break the bonds. Okay, this is basically an endothermic reaction. And when actually what happens when the bonds are formed, okay, that is basically exothermic reaction. Okay, I'll discuss that afterwards in detail. So now let's move further towards the examples of exothermic reaction. Remember one thing: freezing, freezing of ice, freezing of water, you can say. So in freezing of water, you are moving from liquid to solid state. Can you please tell me which is having more energy, liquid or gas? Yes. Which is having more energy, liquid particles or solid particles?
Yes.
Sorry, liquid particles or solid particles? Which is having more energy? Yes, yeah.
Liquid.
Yes. So it is at higher energy, and the solid particles, they are basically at low energy. So what happens as we are moving from high energy particles to low energy particles? So what happens? uh, Energy is released, heat is released into the surrounding. So that is basically an example of exothermic reaction. Now let's move further towards another example, which is condensation. Condensation. So in condensation, what happens? You are moving from gas to liquid state. So can you please tell me which is at high energy? Gas particles. Okay, so they are basically at high energy, and you are moving towards low energy. So in moving from high to low energy, energy is released. Here energy is released. Okay, so when energy is released, that is basically an example of exothermic reaction. Next, uh,
Sir,
yes, Peter.
can we end the class at 8:30 instead of 8:40?
Okay, okay, okay. Uh, let's move further and let's discuss about some more example of exothermic reaction. Remember burning, okay? Burning of uh, anything you can say that is basically an example of exothermic reaction. Let's discuss the example of burning of magnesium. We know when we burn magnesium, magnesium burns with a white flame. So magnesium burns with a white flame. So when magnesium is burned, or you can say it can be magnesium or can be CH4. CH4 is methane gas that we are burning in our home. So burning of magnesium or burning of CH4 gas, that both is basically an example of exothermic reaction because a large amount of energy is released. A large amount of energy is released to the surrounding. Of energy is is released into the surrounding. Okay, so they basically belongs from the examples of exothermic reactions or endothermic reactions. So now let's move further towards heat of a reaction. This is our next topic, and that would be heat of reaction. This is heat of reaction. Okay. Okay, so the amount of heat energy, the amount of heat energy given out or taken in. When we give out energy, when there is an exothermic reaction, and when we take in energy, that is basically endothermic reaction. So the amount of heat energy given out or taken in during a chemical reaction, a chemical reaction is called enthalpy change. Okay, so it's basically the amount of heat that is being given out when it is an exothermic reaction or taken in when it is an endothermic reaction. So that is basically called to be as enthalpy change, and uh, the symbol to represent enthalpy change is delta H, is delta H. And the unit of enthalpy change, the unit of enthalpy change is kilojoules. Okay, that is kilojoules. So the important thing that we must need to memorize is basically its definition, enthalpy change definition. And the second thing that we have to memorize here is basically its units. And we need to remember its definition as well. Okay. So this is basically enthalpy change. And now the important thing for us to memorize is that delta H is negative for exothermic reactions and delta H is positive for endothermic reaction. Okay, this is often asked in the exams as well. So you must need to memorize that delta H is negative for exothermic reactions and it is positive for endothermic reactions. We can like take some of its examples as well. Like for example, magnesium, which is in solid state, some more room, when it reacts with HCl in aqueous form, we know it would be producing magnesium chloride plus hydrogen gas is released. So this enthalpy change for this is minus 462 kilojoules. Now, this is first reaction, and this is second reaction in which calcium carbonate is basically broken down or decomposed to form calcium oxide plus carbon dioxide gas is released. Okay, so this is basically delta H for this is plus 222 kilojoules. Okay, I just want to emphasize on this thing. If you can see the enthalpy change for this reaction, so you can see it is negative. That basically shows that first reaction is basically let me just write it for you. So this reaction, if delta H is negative, so this reaction shows that it is basically an exothermic reaction. And you can see that for this reaction, we actually know that decomposition of a compound that is basically endothermic reaction. But there's an evidence that when we see its enthalpy change, the value is said to be positive. So if there'll be positive value, then we must know here that the way this should be endothermic reaction. Okay. So it becomes quite easy for us to understand. Okay, so let's move further. Okay, so now our next topic is basically, Ayan, is there any question up till now? Yes,
No.
Ayan. Okay, so I hope everything is clear to you. Now let's move further. How are chemical bonds related to heat energy? Heat energy. Remember one thing, when uh, two atoms, two or more atoms, they combine, okay? So when two atoms combine. What we mean by combine? That means bond is formed. That means bond is formed. And we know that formation, bond formation is basically, we have already discussed this thing, bond formation is exothermic reaction, is exothermic reaction. So bond formation is
Sir.
exothermic. O- Okay, so bond formation is basically an exothermic reaction. Okay, so like for example, we have, this is hydrogen atom and this is another hydrogen atom. When they both are combining, so they are basically forming a covalent bond. So what happens, that heat energy is given out during this process. Heat is given out. So what we mean by that, that there is a bond formed which is H2 molecule, and this process is termed to be as exothermic reaction. So heat energy is basically released during this process. Moving further, now there is a reaction in which what happened, this is basically oxygen molecule and that has been broken up. We know that it has been formed by a double covalent bond, this molecule. And when this bond is broken, so what happens? Heat energy is absorbed. We know that during bond breaking, heat energy is absorbed. So what happens because of that oxygen molecule that would be broken up into oxygen atom and there is another oxygen atom. So this is oxygen atom and this is another oxygen atom. So this process is basically an endothermic reaction. Reaction. Now, let's move further and let's discuss about uh, bond enthalpy. Okay. Yes, Yan. Is it clear up till now?
Yes.
Okay. So let's move further towards bond enthalpy. Now, we are given with the bond enthalpy of different bonds, okay, that are being formed or are being broken. So let's first discuss this question. We are given with the question, and that is like there are basically covalent bonds here, covalent bonds. This is bond enthalpy, and this is a very important question that is often asked in the exam as well. So they have given us the like this is for hydrogen bond and bond enthalpy, which is being measured in kilojoules per mole. So how much bond enthalpy of is basically for this reaction? They are given us with 436 kilojoules per mole for hydrogen bond. Just Okay. So there was a question which they have given, which hydroxide covalent bond. Okay, and its bond enthalpy is basically 463. Now, oxygen double bond is basically 496. So this is basically the question, and it's very important question that is oftenly asked in the exam as well. So you first need to consider these bond enthalpies. Okay, so how does they basically ask the question from us? The question is that they have given us the chemical reaction, and that is 2H2 plus O2, okay, and they are basically form 2H2O. Now, what actually is happening? This is, we know that it contains hydrogen-hydrogen bond, and this contains oxygen-oxygen double bond. On the other hand, there are basically two water molecules, and each contains uh, the bonds like this. Each contain two hydroxide bonds. Okay, these are two hydroxide bonds, and there is an other water molecule which contains another two hydroxide bonds. Okay, then now what happens? They are going to give us the question that we have to find overall heat change, or you can say enthalpy change. So find out enthalpy change. This is basically the question. So what is basically the formula to find out the enthalpy change? And that is basically uh, enthalpy change delta H is equal to total heat energy absorbed for bond breaking, total heat energy absorbed for bond breaking minus total heat energy, this is sorry, total heat energy released released during bond formation. Remember this thing, that total heat energy absorbed for bond breaking, that bond breaking occurs on left hand side of equation, and total bond heat energy released during bond friction formation, that occurs on right hand side of equation. Okay, so now we have to calculate total heat energy absorbed for bond breaking. So that is on left hand side, and that contains basically 2 uh, multiply with its bond enthalpy. So what is the bond enthalpy for hydrogen? Hydrogen, that is 436. So we are going to multiply it with, yes, we are going to multiply it with, yes, Ian,
Multiply it with 40.
multiply it with 2, because there are two
2.
hydrogen bonds. So what is the bond enthalpy of hydrogen bonds? That is 436. So 436 has been multiplied with it, because there are two hydrogen bonds. Next, we are going to add what? We are going to add oxygen. How many oxygen molecules are there? So there is only one oxygen molecule that you can see here. There is only one oxygen molecule. So you are just going to add its bond enthalpy. That is 496, and then you are going to subtract it. You are going to put the bracket for the right hand side. There are basically How many water molecules are there? So you're going to multiply it with 2, as there are 2 water molecules. So how many hydroxide are basically present in one water molecule? And that is basically, we know that 2 hydroxide are basically present in one water molecule. So what is basically its bond enthalpy? That is 463. 463. Is that clear, Ayan? Yes, Ayan. Is that clear?
Yes, sir.
Okay. So this is for left hand side.
Yes, sir.
Okay. Let me just mark it. This is for left hand side. Left hand side, I'm going to mark it for with green color. And right hand side, I'm going to mark it with, you can say, orange color. Okay. So this is for right hand side. This is for bond formation, and left hand side is basically for bond breaking. Now, we are going to calculate it. Okay, so let's calculate it. Ayan, please take out your calculator and tell me what is the answer when we are multiplying 436 with 2.
872.
872
72.
plus 496 minus. Now, multiply 2 with 463. Yes.
Yes, sir.
Multiply this 2 with 463.
Yes, sir. It's 872.
No, are you sure? 2 multiply with 463. 2 multiply with 463.
2 multiply 463. 926.
926. Okay. So let's move further and let's discuss about, just make it bigger. It's 4926. Okay. Now, please add both of them, this one and this one. Yes, add both of them. Yes,
872 plus
plus 496.
496.
Yes,
1368.
1000.
1368.
1368
68.
minus 2 multiplied by 926.
Yeah.
Yes, what is the answer?
2, 2, 2 multiplied 926. 1852.
1852. Now tell me the final answer.
484.
484. And the sign would be of minus 484 kilojoules. So this is basically our bond. You can say this is basically the enthalpy change. So remember, this is minus. Remember, enthalpy change is negative for which reaction? For exothermic reaction. So in this way, we'll be able to know that the reaction between hydrogen and oxygen is basically an exothermic reaction. Why? Because enthalpy change that comes out to be negative. Okay. So in this way, we will be able to guess that enthalpy change is basically negative. So this reaction is exothermic reaction. And for endothermic reaction, always remember enthalpy change would be positive. So let's move further towards activation energy and let's discuss about the concept of activation energy. Okay, so let's start with this concept of activation energy. So, Okay, this is activation energy. So first of all, I'm going to write about the definition of activation energy, and that comes out to be the minimum amount of energy required to start a reaction. To start a reaction is called activation energy. Is called activation energy. Okay, so this is basically the minimum amount of energy that we must provide to the reaction in order to start a reaction. For example, we have methane gas. Okay, we have methane gas and oxygen. We know that they basically react to form CO2 plus 2H2O. Okay, so this is the reaction. And remember one thing, this reaction does not take place on its own. Okay, so what we need to do, we must need to provide it some activation energy to start a reaction. So that is why what we are going to do, we are going to provide it either with an electric spark, either with an electric spark, or either oh sorry,
Sir,
yes Peter.
just give me 2 minutes, I'll come back.
Just stay here, please, because I just need to finish this lecture, and this would be finished in just a bit. So either we need to give an electric spark, or either we can give it a burning splint. Okay. So these two things for this reaction would provide them with the activation energy. So these two things would provide the activation energy to start this reaction. Okay, so they would provide the activation energy to this reaction. Okay, so in this way, activation energy plays a very important role. So first of all, let's move further and let's discuss about some of the concepts which are related to exothermic reactions and endothermic reaction. So we are going to study basically its energy profile diagram. That is very important. So this is energy profile diagram for exothermic reaction. So first of all, let's discuss about energy profile diagram for exothermic reaction. Okay, so first of all, there's a graph that we are going to plot like this. Remember, for exothermic reaction, we know that heat energy is released. For exothermic reaction, heat energy is released. So reactants will always, first of all, this is basically energy that we are going to put here on x-axis, and there is basically the direction of reaction. So a graph is basically plotted between both of them. And as we know that for reactants, they would be having more energy because heat energy is released in this process as compared to the products. So the reaction would comes out to be like this, the diagram, while the reactants, they basically products, they are basically at the lower end. So these are basically products and these are basically reactants. Reactants are at higher energy while products are at lower energy. Now, in this, you can see one thing here. Like, just want to describe one thing that from here till this point, this is basically called to be as the activation energy that must be provided to the reactants in order to start the reaction. So this is basically the difference between both of them, and that is basically the activation energy that must be provided to the reaction in order to start the reaction. So activation energy is very important in this diagram. Activation energy. Mhm. Just wait. Okay. So activation energy is quite important for us to understand here that what is the activation energy in this diagram which represents for the you can say it that represents for the exothermic reaction. Okay. So EA must need to be find out and it is basically at this place. Is that clear, Ayan? Okay. Hello, Ayan, is that clear?
Yes, sir.
Okay, now moving further towards that, which is basically the enthalpy change. Enthalpy change is basically the difference in the energy of the reactants and the product, and that basically lies at this place. It is basically at this place between the energy difference in the energy of the reactants and the product. Remember that enthalpy change is negative, okay, is basically negative and always pointed in the downward reaction and always pointed in the downward. Okay, so you must need to remember these things. So if we use catalyst, the function of catalyst is basically to increase the reaction by decreasing its activation energy, by decreasing activation energy. If we are going to use the catalyst, so graph formed would be like this. So you can see that the activation energy with the use of
Okay,
catalyst,
sir. Can you give me 2 minutes? I'll come back on.
okay, that would basically decrease. This is activation energy and that is for catalyst and that is going to decrease. So this is basically the activation energy for the catalyst. Okay. Okay. So this is for exothermic reaction. Oh, just this is for exothermic reaction. Now moving further towards endothermic reactions. Now let's make the energy profile diagram for endothermic reaction. For exothermic reaction, we know that reactants are basically at higher energy while products are basically at lower energy. But for endothermic reaction, heat energy is absorbed. Okay, heat energy is basically absorbed. Heat energy is absorbed. So what happens? Products would be at more energy. Products would be at more energy. They are reactants They are basically products. Okay, this is energy of the reaction, and this is basically the progress of the reaction. And we know that products are basically here at higher energy level. So activation energy would be from this point till this point. This would be the activation energy for the reaction. Enthalpy change would be positive, and that would be directed from the bottom, from where this reactants energy is, and that goes towards the top like this. And this is basically enthalpy change, and that would always be positive. Okay, that would always be positive for this endothermic reaction. And if we are going to use catalyst, then it would become like this. And now activation energy for catalyst would be this. This is basically activation energy for catalyst. So this is basically the whole concept which is related to endothermic and exothermic reactions.